Students, today we are doing the lab called the properties of matter. And I've got a couple of beakers here boiling. In one of those beakers, I am going to put some stearic acid. And stearic acid at room temperature is a solid. You can see, what was that? You can see that stearic acid at room temperature is a solid. And what I'm going to do is continue boiling that until it's all melted. And then we are going to do a cooling curve for stearic acid versus water. We have a thermometer in the stearic acid. We have a thermometer in the water. And when this is completely melted, I will remove the entire beaker from the hot plate, and we will take data for 30 minutes, taking the temperature of the stearic acid and the temperature of the water and seeing what that data tells. Okay, so that's what's happening in here. In this beaker, I'm going to place potassium nitrate. I'm going to skip the 20-gram one because it just takes too much stirring and half the time we break a test tube. So I've got 3.5 grams of potassium nitrate in here. I've got 5.5 grams of potassium nitrate and 10 mils of water in here. I've got 10 grams of potassium nitrate and 10 mils of water in here. And I've got 15 grams of potassium nitrate and 10 mils of water in here. And what I'm going to do is I'm going to stir them, and I'm going to use a different stirring rod for each one. I want to get all of that stearic acid to dissolve. The 3.5 is already dissolved kind of on its own, no problem there. The 15-gram one is going to take me a while to stir it up. So we're just going to let it be for a bit. And each time I need to, let's see, the 3.5 is stirred up. I'm going to stir a little bit in the 5.5. And the 15-gram one is going to take a lot of stirring. Quite often in lab, students will break a test tube when they're trying to stir that 20 mil one because it just takes so much stirring. Anyways, with this we will generate a solubility curve. And with this we are going to generate a cooling curve. You will be graphing both of these. You will be graphing data from both of these. Now, this one, as you can see, is almost completely liquid. We need to wait until it's completely liquid. So this lab on the properties of matter, we're going to learn about some of the properties of matter. We're going to learn about density. We're going to learn about the heat of fusion. We're going to learn about melting points, boiling points. These are all different properties that various items possess that help us figure out what is it that we're dealing with. Okay, so like lead has a particular density. It's very dense, whereas aluminum has less of a density. And we can look at things like color. We can look at things like boiling point, melting point, freezing point. All of these things are what we call properties of matter. Just going to look at this a little bit longer. And it looks like it's completely melted. And so what I'm going to do is place it on the table. And this will be my 0-minute reading. And we're going to take reading for 30 minutes. As we take the readings, we're going to note in the test tube how much solid we have in the test tube and how much is still liquid. Right now, in our first reading, it's 100% liquid. And the water, of course, is also liquid. At room temperature, this becomes solid. Is water at room temperature a solid? No. So we know that water, the data, it's just going to keep getting cooler and cooler and cooler. But at the freezing point, at the point at which this goes from a liquid to a solid, what we will notice with the temperature is that instead of cooling, instead of this going down in degrees, all of that extra energy is going to be used to form bonds that turn this from molecules that flow past each other, which is a liquid, to molecules that are in a matrix and simply vibrating, which is a solid. It takes energy to do that, and that is what the heat of fusion is. That is what it's a certain amount of energy that it takes for something to go from a liquid to a solid, or from a liquid to a gas, or from a solid to a liquid. So whenever there's a change of state, whenever something changes state from liquid to gas or gas to liquid, there is energy released or energy absorbed. And that's kind of what this experiment is going to show. And I am going to provide the data, but we're going to be looking at this periodically to see if there's any solid forming yet. We started at 100 degrees, now we're down to 98, no solid yet. When we reach the point where it goes from liquid to solid, we're going to see that instead of this continuing to decrease in temperature, like the water will, we're going to see it stabilizing at that certain degrees. It will stay at that degree level until all of the liquid is gone. It's like if you take an ice cube and you put it in some water, that water is going to stay at 0 degrees once if you've got a whole bunch of ice, until all that ice is melted. The temperature of the water will not change. You can try that, a little experiment. So what we're looking at is changing of state and how much energy it takes. When something has a very strong or a very high heat of fusion, a very high measure of how much energy it takes to change state, we say that there's very strong molecular bonds holding that form or must be broken in order for it to change state. And in lecture, we'll go over that a little bit. Hopefully, it'll be made a little bit more clear. For now, we're going to leave this alone. Like I said, I'm going to provide the data. When it starts to form a solid, we'll come back to it. We'll note the temperature, and we'll continue. Now, let's look at our potassium nitrate here. That's going to generate our solubility curve. I'm going to keep stirring. We still don't have everything dissolved. The 3.5 is all dissolved, almost completely dissolved. I'm going to just stir that up. What we need to do is get it completely dissolved so that we can take this off the heat as well, and we can start to wait and see when this is all dissolved, it's just going to be a clear liquid. When we reach the point where that amount of potassium nitrate in 10 mils is going to start forming into a solid again, when we reach that point, we will take the temperature. And we're going to do it for the 3.5, the 5.5, the 10, and the 15 grams. We'll record that, and then we will make a solubility curve. We're going to leave that also for a second. And we're going to look at basically the 4 parts of this lab that we'll be dealing with. Okay? The first is density. Density is so interesting. Molecules themselves have various densities. A molecule of water has a different density than a molecule of carbon dioxide because they're made of different atoms. When water freezes, the H2O part, the molecular part, the 2 hydrogens and 1 oxygen, they still have the same mass and they're still the same size. But now they're arranged in a different configuration, and so there's a different density of ice versus liquid water. And water is the one substance that is so unique. What do you know about solid water? Does it float in liquid water or does it sink? If I had a bar of gold and I dropped it into a bucket of liquid gold, automatically you know that's going to sink because solid is almost always more dense than liquid. In the case of water, what's so special about water? Water is the most important compound because when it freezes, it doesn't sink. If it did, our lakes, our animals in ponds would all die. But instead, it freezes and creates this nice layer of insulation over the lake. So water is something really, really special. Okay, density equals mass divided by volume. When we take the volume, we're going to be using these graduated cylinders. One is glass and one is plastic. And what's interesting about when we measure with a glass graduated cylinder is that the water molecules are attracted to the glass, and so they will form this little meniscus. When we take our measurement in the glass one, we are going to use the measurement at the bottom of the meniscus. That will give us the actual volume. So let's find the volume of 4 things. I'm going to give you the data, and you are going to use this data in the density data table. This is a piece of aluminum. So our first thing we're going to do is aluminum. The mass of this piece of aluminum, and remember significant figures, and the mass is 95.55 grams. How many significant figures is that? 95.55 grams. That is the mass. So let me write that on the board. Aluminum, we have 95.55 grams. We are trying to find the density of aluminum. Let me see if this one will fit in there. It will not. I've got one, actually, I have got, for some reason, I did not go to 200. So let me just put a little more in here. We want to start out with a nice even number. Okay, I have 200 milliliters of water. Now, this is not a regularly shaped object. And so to find the volume, we can use water displacement. Okay, so I'm going to take this. I'm starting out at 200.0 milliliters. I put this in. I make sure I don't splash. I started out at 200.0, and wow, it's at 10, 20, 30, 240, and literally it's at 240.0. So if I started, I went from 200.0, so my total mass, my total displacement is 40.0 milliliters. Now, you are going to do your calculations and you're going to find the density of this aluminum. Okay, 95.55 divided by 40.0. How many significant figures can you have in your answer? You've got 4 here, you've got 3 here. So how many can you have in your answer? That should be how many you have. That should be how many you put in the data table. All right, now we're going to find the density of this piece of plastic. Let me use a smaller piece so that I can use the glass. Okay, we're going to find the density of this piece of plastic. First we have to find the mass. 5.85 grams. Okay, the plastic. 5.85 grams. Now we're going to use, this is almost, we could almost use length times width times height with this, but it's a little bit not exactly right. So we've got 100.0 milliliters. Oh no, it floats. What are we going to do? It has a density less than water. So what we have to do, so water has a density of 1 gram per milliliter. So we've got to kind of hold it down, but we don't want to get this wood in there. So I'll try to get the wood right at, and we are right at 109. So we started with 100 mils, and we went to 109, and it was 100.0, 109. So this is 9 mils. It was right at the 0.0, so I'm going to add the 0.0, 9.0 mils. So when you do this math, you should get a number less than 1 because it floats in water. Water has a density of 1. Do you know that if we had a bathtub big enough for the planet Saturn, that it would actually float? Because Saturn has a density less than 1. It's one of the gas giants. We'll get to that when we do our planets, but it's a gas giant, and it's actually, the density of Saturn is less than 1. Okay, so we've done 2. We've got 4 to do. Let's take this piece of granite. Okay, this will be our third piece. This piece of granite has a mass, and I need to stop breathing on this. 56.91 grams. 56.91 grams, okay. I'm going to have to erase the aluminum. The granite. 56.91 grams. Now again, if it was a regularly shaped object, we could just take length times width times height to find the volume. But because it isn't, we have to use water displacement. I don't have to dump this out and start over because I have enough room to put this in. We are at 210, 20, 30, 40. We're at 240.0. It is literally right at, I did not plan that, but we start out at 240.0. That's what we started out with, and we end up with 255, 260. Again, it's at 0.0. That is very strange, but 260.0 milliliters. We always put our units. So the volume of that piece of granite is 20.0 milliliters. That is going to give you the density of that stone piece of granite. We have one more to do. Again, how many sig figs? This has 3, this has 4. So how many sig figs are you going to have in your answer? You've got to think about that. Now, one more thing we're going to do. We have a piece of lead. This is a fishing sinker, if you're going fishing. Zero that out. Okay, measure this piece of lead. 60.85 grams. Okay, this is going to be the lead. 260.85 grams. Now let's take this piece of lead and let's stick it in here. We went from 260 to 266. So we had, the original was 260.0, we went to 266.0, and so this lead displays 6 milliliters, 6.0 milliliters. How many sig figs? How many sig figs? How many should be in your answer? So what we just did is that first part of the lab, the density of solids. You're going to do the math. I showed you the technique, now you're going to do the math. There's a couple of questions, and what you need to do is just a dimensional analysis question for question 1. And question 2 is kind of a think outside the box. If you had rock salt, you can't use water displacement, because what does water do, or what does salt do in water? Salt will dissolve. So how could you find the volume of a chunk of rock salt that was not, regularly shaped, so you can't use length times width times height? Try and describe a way that you could do that. Finding the mass of that chunk of rock salt's easy. You just put it on the scale. But finding the volume, how could you find the volume of something that actually dissolves in water? What could you do? All right, so that is the first section about density. Now we're looking at our cooling curve. Whoa, look at this. We see now that this has started to form back into solid, and it's right around 68 degrees. So the stearic acid is at 68 degrees. The water is all the way down to 60. They're in the same container. The water is 60 degrees, but the stearic acid is stuck at 68. It's stuck at 68 degrees. What is happening inside the test tube? It is turning from a liquid to a solid. The atoms in a liquid flow past each other. The atoms in a solid are locked in a matrix. Locking those atoms up into a matrix takes energy. So instead of this letting the energy escape into the atmosphere like the water is doing, and the water will continue to do until it gets all the way down to 0, which this classroom's above 0, so we'll never see that water freeze. This will continue to stay at 68, which is the melting point, which is the point at which when we apply heat, this will turn into a liquid. When we take energy out, it will turn into a solid. That's its boiling point or a melting point. It's kind of the same thing. When you're going from a liquid, it's actually the freezing point or the melting point. It's the temperature. When water's at 0, if you add heat, it's going to be a liquid. If you take heat away, it's going to be ice. This particular substance doesn't need to get all the way to 0 for that. This is a solid at 68 degrees. This turns into a solid at 68 degrees. It will stay at 68 degrees until all the molecules are locked into the matrix. Once they're all locked, it will continue cooling. So I'm going to provide you with the data, and you're going to do a graph of the cooling curve of stearic acid versus water. They both started pretty high, and water just continues to go down. But the stearic acid, on the other hand, when it reached a certain degrees, it started to level off. At this temperature, this is the temperature where stearic acid goes from one state of matter to another. Why does it level off? Because instead of that energy, like the water just keeps releasing the energy into the atmosphere, getting cooler and cooler, it'll continue cooling till it gets to room temperature. This will only continue cooling once all of the solid is formed. All the liquid turns into solid, then it will continue cooling. And you'll see that in the data that I provide. And I'm going to provide the data in the data table. You're going to graph the cooling curve. Let's see how our solubility curve is going. We've got the 10 gram one is almost completely dissolved, but the 15 gram, I need to work on that a little bit. So I'm going to stir the 15 gram one quite a bit. And Greg, if you don't mind getting ice out of the freezer, then we will be able to complete this. There's 2 trays. Thank you. So what we're going to do is we are going to, when this is all finally dissolved, we're going to take it off the heat. The 3 and the 5.5 are good. The 10 is almost good. And thank you very much. And we are now working on the 15. Let me lift this up so you can kind of get an idea of what I'm up against here. So I've just got to get the rest of this dissolve, and then we can start getting our data for our solubility curve. So with the stearic acid, we did our cooling curve, and with the potassium nitrate, we are going to get our solubility curve. Believe it or not, in these test tubes, it will actually start to snow. Hopefully we'll be able to pick that up with the video camera. Once it reaches the temperature, what we're doing is some of these are more saturated than others. And so have you ever known someone who puts a lot of sugar in their coffee or their tea, and then they drink it real slowly, so eventually when they're all done with their cup of coffee, there's a bunch of sugar on the bottom? So when it was hot, that coffee could hold all the sugar in solution. But as it cooled, as the molecules started moving slower and slower, some of the sugar falls out of solution, and that's basically what we're doing here. Okay, so I've finally gotten to that point, and I'm going to move this back, and I will put the container here, and I'm just going to unplug the hot plate. I do not want to touch it because it's super hot. Okay, now one of these has 15 grams in 10 mils, one has 10 grams in 10 mils, one has 5.5 grams in 10 mils, and one has 3.5 grams in 10 mils. And by the way, I did not mention the boiling stones. We have some boiling stones in here. Some of you who might be cooks or chefs, you know that often things that are boiling can bubble over, but if you put a little, usually they sell them at Bed Bath & Beyond or whatever, they sell a little boiling stone you can put in the bottom of your pot so that things don't bubble over. Okay, so we're going to be watching the 15. I've got a temperature right now of 93 degrees, and we're going to watch this because the 15 gram one has way more solute in the solution. This is going to be the one that will start snowing first. And let's see when we reach that point where we've cooled it enough, that it will start to snow in here. So I'm going to speed up the process a little bit some ice so we can get this cooling going. Make the water a lot cooler. And we are looking at the 15-gram test tube, hoping that we will reach the point at which 15 grams in 10 mils of water will start to fall out of solution, we call it. Okay, I think I see something going on. Not quite yet. I will use another ice cube here. We're going to speed this along. I will provide the data for this as well, but I do want you to see how we got the data. Okay. So I'm going to put another ice cube. I'm trying to cool the water down faster so that we can get the desired effect. 15 gram. Let's see if I just take it out. Not quite yet. Let's cool this down some more. Now, normally in lab, you would be sitting here staring at this for probably 10 minutes. So we're just speeding the process up using some ice. And we are almost there. I'm going to put this right next to the ice. Once it starts coming out of solution, we'll record that temperature. We'll record the temperature for the 15, the 10, the 5.5, and the 3.5. And at that point, we will have enough data to come up with a solubility curve. Now, can you see that it's actually snowing inside the test tube? So we reached the point, and that was at 61, but I will give you this data. We reached the point where the 15 gram is now going, the potassium nitrate is now coming out of the solution. Okay? It's now going from liquid to solid. The next one that this would happen with is the 10 gram, and then the 5.5 and the 3.5. I'm just going to show you again. This is the 15. It's going from liquid. See how it was? It was liquid, and now it's going into the solid because we've reached that temperature. Now, with this data, you're going to make a solubility curve of potassium nitrate. Amount of potassium nitrate in grams, so you'll have 3.5, 5.5, 10, and 15. Make sure that you use a good scale here, a good range. Okay, you're going from 0 to 15. Temperature in degrees Celsius, you'll look at the data, and then you will put that here, and you will make your solubility curve. I will provide the data for that. All right, so that is our solubility curve, and now we have one last part to the lab, and with that I will use some marbles and some BBs. These are just, little BBs from a BB gun, marbles. And the marbles and the BBs are going to represent alcohol and water. Water is made up of 2 hydrogens and 1 oxygen. That is what makes up a molecule of water. Alcohol, this particular ethanol that's in the question, 3 carbons, C3, 1, 2, 3, 4, 5, 6, 7, 8, C3, H7OH. That is the chemical formula for the alcohol. So what we're going to do is the very last question in this lab talks about a situation where we've got alcohol, isopropyl alcohol, mixed with distilled water. Okay? This is going to represent the alcohol, the big molecule. Molecules of alcohol are large. They're not big as marbles, right? When we look at things on the atomic scale. They're extremely small. But water molecules are even smaller. Okay? So the last question says, isopropyl alcohol is completely soluble in water, meaning if I add alcohol to water, it's completely soluble. It will distribute itself in the water. If we mix 50 grams of isopropyl alcohol, and it gives the density, so you need to use that formula to find out how many milliliters of isopropyl alcohol 50 grams is. That'll be a dimensional analysis problem. You mix that with 75 grams of water. What is the expected volume? So you're going to add 75 milliliters of water, because water has a density of 1 gram per milliliter. So if there's 75 grams, there's also 75 milliliters. But you have to find out how many milliliters of alcohol. Now, I'm going to do a little demonstration to help you. And I added 70 milliliters of alcohol, of water, to 100 milliliters of alcohol, and I should get 170, but I don't. You can see that these little water molecules are kind of tucking themselves in around the marbles, around the alcohol molecules. So this question says, when the solution is produced, the measured volume is 131 milliliters, which is less than what you expected. Just like this is less than if I added 100 plus 70, I should have 170, and I only have 150 mils. Why? What happened to those other milliliters? Why didn't it add up? And you have to think about this picture. What's going on with the little water molecules? Are they taking up as much space as they did when it was just water molecules? Look at how they're fitting in between the marbles. They're squeezing into tight spaces. Think about that when you're answering the last question. So, the Properties of Matter lab is basically 4 parts. You're going to be doing the density calculations. You're going to be producing a cooling curve with the data that I give you. You're going to be making a solubility curve, and you're going to be doing this very last problem. That's the whole lab. Make sure if you're going for the A on the lab that you answer the questions scientifically. Like, for example, that last question, I should see these diagrams on your lab if you're going for the A. I should see scientific thought. I should see measures or discussion of the heat of fusion when you're talking about why did this level out. I want you to, if you're going for the A on the lab, you need to use scientific terms and you need to go into some detail. Thank you.